We're all familiar with Sir Isaac Newton's three laws of motion. Newton's first law states that a body at rest remains at rest, and a body in motion remains in motion in a straight path unless a net force acts on it. Without restraint, these crash test dummies are hurled forward in simulated accidents. Newton's second law states that the acceleration of a body is proportional to the net force acting upon it and is inversely proportional to its mass. Drag racers need rapid acceleration off the starting line in order to win a race. In more familiar terms, the net force equals mass times acceleration, F equals ma. Or more properly, the net force equals the time rate of change of the linear momentum of an object. Newton's third law states that when a body exerts a force on a second body, the second body exerts an equal and opposite force on the first body. The force that propels this rifle bullet acts in reverse on the gun, causing recoil. All three of Newton's famous laws apply as well to fluid flows as to solid objects. In fact, Newton's laws are the foundation of fluid mechanics. In this CFD simulation, three solid spheres fall through a pipe full of fluid. The solids exert forces on the fluid, and the fluid exerts equal and opposite forces on the solids. Both the solid spheres and the fluid particles accelerate due to these net forces acting on them. When an object generates a lift force, as in this simulation of a fly flapping its wings, fluid particles are pushed in the opposite direction, downward, due to Newton's third law of motion. We can see this downwash clearly when smoke makes the flow around a bumblebee visible, or the flow around a butterfly in flight. The same thing happens with man-made flying objects like this helicopter simulation. A lift force is generated on the rotor blades by the air, and at the same time the blades push the air downward. The footprint, so to speak, of the helicopter is produced by its downwash on the water surface below. In another example, the rocket engines of the Space Shuttle generate enormous thrust, based on Newton's second law, by accelerating fluid particles to high speeds in the direction opposite the shuttle's motion. When water flows through the spray nozzle suspended at the end of a garden hose, it imparts momentum to the outside wall of the nozzle and generates thrust when the water exits rapidly. The combined effects force the nozzle backward until there is enough strain in the hose material to cause an equal resisting force. When we stop the water flow, these forces relax and the nozzle returns to its original position. Here, a jet of shop air impinges on a scale. We can see the airflow using the Schlieren optical method. The air jet impinging on the scale produces a measurable force, shown by the digital readout, since all of its momentum is transferred to the plate on the scale. Here's an appropriate control volume to analyze this process. A sum of the forces and the momentum fluxes in the vertical direction using the Reynolds transport theorem and Newton's second law of motion reveals that the reaction force measured by the scale is simply equal to the momentum flux coming out of the nozzle. The momentum flux of a fluid is the product of its velocity and mass flow rate. Thus, we can get about the same momentum from a high-speed jet of a light fluid like air as from a slower jet of a dense fluid like water. There are many interesting and useful examples of such momentum control volume analyses. Here's one showing a control volume for a wind turbine. If we know the wind speed and power output, we can analyze the forces on the wind turbine and determine its efficiency. In this case, a ping-pong ball is suspended in a jet of helium. The sum of the forces involves the weight of the ball acting against the upward pressure and viscous forces produced by the jet. How does one know where to draw the control surface for a given problem? This comes with experience, but here's a simple example, a water faucet. We could draw a control volume that exactly surrounds the water flow, but analyzing it requires boundary conditions that are not easy to figure out. A simpler overall approach is to include the entire faucet in the control volume and simply slice the flow perpendicular to the inlet and the outlet. Angular momentum transfer from solid objects to fluids is analyzed in much the same way as is linear momentum transfer. In this CFD simulation, a ball is spinning as it drops into a pail of water. It transfers angular momentum to the water, which begins to spin around inside the pail at the expense of a decreasing spin rate of the ball. This water sprinkler uses most of the incoming water momentum in the hose to spray the water on the lawn. A little of the momentum, though, is used to rotate the sprinkler by orienting the nozzles at a slight angle with respect to the center of rotation. If one increased the angle, the sprinkler would turn faster. Old-style paddle wheel steamers are propelled by the blades of the paddle wheel pushing water backwards, which yields a forward reaction force. At terminal velocity, a parachute produces enough drag force to exactly equal the total weight of itself and of the person suspended beneath it. This centrifugal blower is a radial flow turbomachine. Air enters in the axial direction, turns radially through the blades, collects in the scroll, and discharges tangentially. Both linear and angular momentum are transferred from the rotating blades to the air in this complex three-dimensional fluid flow. Here's a simple homemade model rocket test stand that indicates the rocket thrust by the deflection of a spring-loaded pointer. An equilibrium position is achieved when the spring force exactly balances the thrust. Many airplanes have clamshell-type thrust reversers that close in the jet exhaust and deflect it slightly forward, thus providing a component of reverse thrust to slow the aircraft upon landing. Finally, a jellyfish draws in surrounding water and expels it backward using its momentum to provide forward thrust. During intake, water is drawn in from all directions with negligible thrust compared to that of the highly directional jet of expelled water.